Hello, chemistry students. Today we're going to be talking about electromagnetic spectrum and how it relates to hydrogen emission spectra, which we'll get to in a little bit. So first things first, let's refresh ourselves on the electromagnetic spectrum. I'm sure you've seen this before, probably in physical science, but basically all wave energy is classified in the electromagnetic spectrum. And so when we look at this, we have some of so before we discuss that, we need to talk about a wavelength. And so what a wavelength is, we have a wave. Okay. So if I go from peak to peak, I could go from trough to trough, I could go from middle to middle, it doesn't matter. But the distance between two waves is referred to as the wavelength. Makes sense. It's the wave and it's the length of the wave. Frequency is how many times a wave passes in a given amount of time. So let's say this wave here that I drew took 2 seconds. Well, if I have a wave that looks like this, which I don't like, so I'm going to draw again, this wave has a frequency of 3 waves per second. So something to know about this is that the more waves there are per the amount of time, so the higher the frequency, the more energy is required. I usually give the example in class, think of like a bunny hopping. If a bunny's hopping at a nice slow pace, then it's going to have less frequency, less jumps, in that amount of time, it's going to expend less energy. But if a bunny is running from something and it has a lot of hops in a short amount of time, it's going to expend more energy. So basically, what we're trying to get from here is that wavelength, and this is our lambda symbol, so for wavelength, it's a lambda. And so the longer the wavelength, so the higher or longer the wavelength, the lower the frequency. And therefore, the lower the energy. So, high wavelength, low energy. The shorter the wavelength, the higher the frequency. So that means we're going to require more energy. Okay? And so we look at our electromagnetic spectrum. There's all kinds of waves that are on here. And so we notice that on our longer end of the spectrum, or our lower energy, so longer means lower energy, shorter means higher energy. And so things like radio waves, microwaves, yes, like that thing in your kitchen, infrared, those are all low energy waves. And that makes sense because we don't usually think of those as harming us. We're not concerned about how many radio waves we're exposed to because it could damage our DNA. And that's because the energy is low enough there that it can't penetrate our cells in our body. However, when we look at the other end of the spectrum, ultraviolet, X-rays, and gamma rays, ultraviolet like the rays from the sun, X-rays like what you get to see your bones if you have a broken bone, and gamma rays, those have high energy waves, and those waves can penetrate our cells and can get in and damage our DNA. So the high energy waves are usually the more dangerous waves. The low energy waves are less dangerous waves. The part that we're going to focus in on is you should notice visible light. Visible light makes up a very small amount of the entire spectrum, but it's what we can see, so that's what we usually talk about. And so you should notice that on the longer end of the wavelength, or on the lower energy end, is our red. I'm going to, real quick, give me just a second. I'm just going to get rid of this because I want to use that space. Okay, so over on the lower end, less energy is red. Then we have our orange. We have our yellow, we have our green, we have our blue, we have our indigo, and we have our violet. And so you know this is your Roy G. Biv. So you're familiar with the electromagnetic spectrum. You've learned the colors of the rainbow. And so this is what's causing the colors of the rainbow, why they're different colors. They're different wavelengths of light. And so our eyes detect the different wavelengths of light as different colors. So why is this important? Well, we're going to talk about hydrogen. And so let's remind ourselves about hydrogen. Hydrogen has an atomic number of 1, so it has 1 proton, 1 electron, and it has a mass of 1, so that means it has 0 neutrons. And so, some experiments were done with hydrogen specifically because it has 1 electron. We wanted to learn the behavior of the electron. And so, what they did, I'm going to erase this for a second. So what they did is they fired high energy beams of light at this electron. So this is kind of like our modified Bohr. I'm just going to do it as a really long Bohr here because we're gonna go over some stuff. So I've got energy level, energy level, energy level. Oops, this one was supposed to be up here. This one was supposed to be up here. And then this one. And then this one. Yes, I'm intentionally not drawing them the same amount of space. It was found out that the energy levels aren't equal distances apart from one another. The further out we go, the closer the energy level is to the previous energy level. And so when we look at this, we're going to look at hydrogen, and hydrogen only has 1 electron. And so like I said, they started firing high energy light particles at hydrogen. And so a photon is what it's called. A photon is a high energy light particle. And the first thing that they learned was that electrons, when we fire these photons at the electron is able to actually jump to a higher energy level. How do we know this? Well, because it's absorbing energy. And in this case, since it only jumps up 1 level, it absorbs a low energy photon. So this is my photon. It's low energy because it has my long wavelength. And the reason why I know it's low energy is because when we looked at this, when you look at this and when you see the light that is emitted from it, it emits a red light. And so that tells us that it is a low energy photon. Our photon is light. So the electron absorbs the photon, jumps up to a higher energy level, and then when it falls back down to its original energy level, it emits that beam as visible light. And so in this case, it emits it as red. So some terms that I said there, let's make sure that we understand this. So absorbed, so when the electron absorbs the photon, absorbs energy, our photon is our energy of light. So when it absorbs energy, our electron jumps to a higher level. Higher energy level. And the reason why we say jumps is because that's exactly what it does. An electron in this case is either on the first energy level or on the second energy level. It's never in between, and so that's very important. So the electron is located on an energy level and can move between energy levels, and can move from one energy level to another. I'm just going to put EL for energy level, from one energy level to another. But never between energy levels. So what that means is that my electron can be here. Ooh, that was the wrong thing. My electron can be here, or it can be here. It cannot be anywhere in between. It's on the energy level, or it's on the next energy level up. So it's on that first energy level, or it's on the second energy level. Never ever between levels. And so then with that, like I said, there was a low light. Well, not all photons are low energy. So sometimes the electron in hydrogen would absorb a slightly higher energy photon. And so that would allow it to jump up 2 energy levels. And how do we know it went to a further energy level? And how do we know it absorbed a higher energy level, a higher energy photon? Simple. Because the light that emitted when we saw the light was green. And as we said up above, green has more energy than our red. So it emitted green visible light. Now, when it comes back down to its original energy level, that's referred to as ground state. So ground state is the electron's original energy level. Okay? So, again, my electron absorbs the photon, jumps up to a higher energy level, emits the photon as a visible color depending on the amount of energy that was absorbed when it returns to ground state, when it comes down. And so this happened again. So another photon came in of higher energy. It was able to jump to a higher energy level because it had more energy, which meant when it emitted the energy, when it came back down to ground state and emitted the energy of the beam was a higher energy beam, and it was blue. Well, there was one more. So we had one more where the electron was absorbed a very high energy photon, which allowed it to jump to an even higher energy level. And when it returned to ground state, it emitted a very high energy visible light. It emits violet light. And I keep saying that when we see this, and you should be sitting there thinking, okay, that doesn't make sense, Dorman, what are you talking about? Well, I'm going to come up here. So this is the same thing that we just went over down below. So up here on my picture, you see you know what, I'm just going to copy this and move it. So here's what my emission spectra looks like. When we look through some special, a special lens that will separate visible light into its colors. It's kind of like a prism. It'll separate this light into its different colors so you can see the different wavelengths clearly. And so when it did it, this is the emission spectra. These are what was seen when it was released. And so we can see that we have the red, which was low energy, the kind of green, which was the middle energy, the blue. The violet's really hard to see in person because it is such a high energy. It's really on that end of the violet end of the spectrum, kind of close to the ultraviolet, and so it's really hard to see. So now here comes the next question is, if hydrogen only has one electron, that means it can only be jumping between energy levels one at a time. Sure, this electron can jump to can jump up one higher energy level and then come down. It can jump up to the second energy level and then come down. But when you look at this spectrum, it's a constant line. There's 4 visible lines and they're constant. They're not flickering. And so how does that happen? How can there be multiple colors, sometimes with different intensities? So the red is really intense, really bright. And like I said, the violet's really hard to see. It's really dim. So why? How does that happen if hydrogen only has one electron? And the answer is actually pretty simple. Yes, hydrogen only has one electron. So here's my hydrogen. I'm just going to kind of draw. I'm not going to worry about my nucleus. I know I'm breaking the rules already, but you're used to it. And I'm going to put my 1 electron. So this is going to be the example of my hydrogen atom. And so I'm hitting it with a photon beam, a photon, and it's emitting light. So like I said, how can it emit 4 beams of light, 4 different energy levels of light, if there's only 1 electron? And the answer is very, very simple. The answer is that when I have these samples, I don't have just 1 atom. I have many, many, many atoms. And so the intensity of the light tells me how many of the atoms are returning to ground state and emitting that color of energy. But the reason I can see all 4 is because I have multiple atoms that are receiving multiple photons. So maybe I have one that's kind of mid. Maybe I have one that's a little bit higher. Maybe I have one that's really high. I have another one that's kind of low. I have another one that's kind of low. I have another one that's kind of low. And so my low ones are going to be my reds. My medium ones, whoopsie. My medium ones will be my green. My slightly higher ones, I want to do another green, sorry. I'm going to say this one's green, kind of lying. I know I didn't put a thing there, but you know what I'm talking about. Hydrogen, there we go. And so, let's show a somewhat high one, but not quite as crazy. And so then these higher ones would be my blue. And then this one, the really high energy, would be my violet. And so I'm seeing all 4 at once because there's multiple different hydrogen atoms that are absorbing and emitting photons. And so that's why I can see all 4 colors at once. The reason why there's different intensities is because there's a different proportion, a different ratio that are absorbing and emitting the different energies of photons. So just kind of like our isotopes. Here I have 1, 2, 3, 4, 5 that are emitting the red energy photon. And so that's going to look brighter to me than the 1 atom that's emitting the violet energy photon. Hopefully this makes some sense, and I look forward to answering any questions you may have. Have a great day.